Welcome to this explainer. Okay, if you've ever stared at a math problem with an x squared in it and just felt this immediate wave of panic, you are absolutely in the right place. Today, we're throwing out the frustration. We're going to treat the quadratic equation like a fascinating puzzle, one that we're going to solve together using one of the absolute most powerful historical tools in all of mathematics, Bhaskara's formula, or as it's known to most of the world, the quadratic formula. Here is our roadmap for today. We'll start with the quadratic problem itself, take a brief time travel through history, uncover the magic of delta, walk through the step-by-step method, and wrap up with some golden tips and graphs. Let's dive right in.
Section 1. The quadratic problem. What are we actually solving?
It's a pretty fundamental question, right? What exactly is a quadratic equation? We see these crazy jumbles of letters, exponents, and numbers on the whiteboard, but what do they actually mean in reality? Before we start throwing formulas around, we really need to understand the beast we're dealing with.
And this right here is the foundation of the whole shebang, the standard form. It's ax squared plus bx plus c equals 0. Basically, every single quadratic equation out there can be organized into this neat little package. Those letters, a, b, and c, they're just real numbers. We call them coefficients. The a is attached to our square term, the b is our linear term, and the c is just hanging out as the independent constant. But listen, there's one absolutely unbreakable rule here. A can never, ever be 0. Think about it. If a was 0, that whole x squared part just vanishes, and then we're left with a basic linear equation. That squared piece is literally the whole reason we're here.
So when a test tells you to solve this equation, what's actually the goal? Well, you are hunting for the roots. And roots are really just those specific magical values of x that, when you plug them back into the equation, make the whole thing perfectly balance out to 0. We're just looking for the exact spots where the equation is totally satisfied.
Section 2. A Brief Time Travel. The millennia-long quest for a solution.
Guys, the history behind this is actually wild. This was a massive global collaboration that took thousands of years. We're talking 1800 BC, where Babylonian scribes were using geometry on clay tablets to solve these spatial puzzles. Then by 300 BC, Euclid in ancient Greece was mapping out visual solutions. Fast forward a bit to 628 AD, and the Indian mathematician Brahmagupta writes down the very first explicit general formula. He even accepted negative roots, which was a huge deal back then. Then, in 1150 AD, another Indian mathematical genius, Bhaskara II, systemizes the whole thing. Finally, in the 16th century, the European Renaissance brings us the modern notation we use today. It's crazy to think about, but this formula isn't just math, it's this incredible inherited human legacy.
And here's a really fun cultural quirk for you. If you studied math in Brazil, you almost certainly know this as Bhaskara's Formula, named after Bhaskara II for his amazing teaching contributions in the 12th century. But, curiously enough, in almost every other country in the world, it's just called the generic quadratic formula. Same exact mathematical power, just a totally different name depending on where you grew up.
Section 3. The magic of delta. Your mathematical crystal ball.
Meet the discriminant. We usually just represent it with the Greek letter delta. The formula is b squared minus 4ac. Now, why do I call it a crystal ball? Well, because before you do any of the really heavy lifting to find the exact roots, calculating just this tiny piece tells you exactly what kind of answer you're going to get. It's a quick little calculation that totally saves you from going down a blind alley.
Let's break down what delta is actually whispering to us. If your delta calculation comes out to a number greater than 0, you are guaranteed 2 distinct real roots. Visually, that means your curve is going to chop right through the x-axis in exactly 2 places. Now, if delta hits exactly 0, you've got 1 real root, a double root. The curve just comes down and perfectly kisses the x-axis at a single point. And here's the best one. If delta is less than 0, like a negative number, just stop right there. There are no real roots. The curve is floating way up above or below the axis, completely missing it. For most high school math, a negative delta literally means you get to drop your pencil because you're done with the problem.
Section 4. The step-by-step. Let's forge your weapon.
Okay, so here is the foolproof, highly recommended method. Seriously, do not try to do this all in your head at once. Step 1, just carefully identify your A, B, and C numbers. Step 2, calculate that delta all by itself. Get that specific number first. Step 3, now that you have delta, plug it into the full formula. That's x equals negative b plus or minus the square root of delta, all divided by 2a.
By splitting it up into these manageable chunks, you dramatically lower the chances of making a silly algebra mistake.
And speaking of mistakes, please watch out for these classic traps. This is where everyone loses points. First off, do not forget the minus sign in front of the b. If your b is already, say, -5, plugging it into the formula means it becomes -5, which flips to a +5. Second, squaring negative numbers. Remember, -3 times -3 is +9, not -9. And finally, that little plus or minus symbol, it's not optional. You literally have to trace two different paths at the very end, one where you add the root and one where you subtract it, to get both of your final answers.
Final section, golden tips and graphs. Let's see this math in reality.
It's amazing how that very first a coefficient entirely dictates the visual shape of your parabola. If a is a positive number, your graph makes a U-shape. It's concave up, kind of looking like a smile. It plunges way down to an absolute minimum point before shooting back up. But if a is negative, the graph flips upside down, like a frown. It rises up to an absolute maximum point and then falls. Connecting the math to these actual shapes is a huge cheat code for double-checking your work.
And that absolute maximum or minimum point we just talked about, that exact spot is called the vertex. And you never have to guess where it is. The x-coordinate is just -b over 2a, the y-coordinate is -delta over 4a. Understanding this vertex is absolutely crucial, because this is exactly what we use for real-world optimization problems, calculating the maximum profit a business can make, or figuring out the exact highest point a launch rocket will reach.
If you're gearing up for standard tests like NM or vestibulaires, write these high-value strategies down. Test makers love to hide quadratics inside word problems. So if you're reading a question and see phrases like rectangular area or projectile's trajectory, alarm bells should be ringing. There is absolutely a quadratic equation hiding in there. Also, use the sum and product rules to instantly check your roots without recalculating the whole thing. The sum of your roots is always -b over a, and their product is c over a. And lastly, get your reps in. You really want to train yourself to smoothly solve a full equation from scratch in under 3 minutes.
So, we've walked through the millennia of history, the foolproof step-by-step methods, and the visual strategies to totally conquer the quadratic formula. But remember, this math does not just live in a textbook. From the perfect arc of a thrown baseball, to the slope of a satellite dish, to maximizing efficiency in the stock market, these parabolas are literally everywhere. So, my final question for you is, how will you spot the hidden quadratic equations shaping the physical world around you today? Keep your eyes open, keep practicing, and thanks for joining me on this explainer.